Picture the bravest thing a human being has ever done. Maybe it's climbing Everest without oxygen. Maybe it's the first step on the moon. Now multiply that by 1,000, and you still haven't come close to what a trip to Mars actually demands. Because every mission ever attempted in human history had one thing in common. The people who left came back. Mars changes that equation entirely. And the more you understand the science, the more you realize this isn't pessimism. It is physics. It is biology. It is the cold, unforgiving arithmetic of space. So let's walk through exactly why anyone who boards a spacecraft bound for Mars will almost certainly never set foot on Earth again. It starts with the journey itself. Right now, as of 2026, Mars sits roughly 188 million kilometers from Earth. That distance is not fixed. It swings dramatically as both planets travel their separate orbits around the Sun. At its closest, Mars is about 54.6 million kilometers away. At its farthest, it stretches beyond 400 million. The only practical time to launch is during a narrow alignment window that opens roughly once every 26 months. Miss it and you wait 2 years for the next one. With current chemical propulsion, the trip takes between 7 and 9 months. One way. So before an astronaut even touches Martian soil, they've spent the better part of a year cooped inside a spacecraft smaller than a studio apartment, hurtling through the most hostile environment imaginable. And during every single second of that journey, something invisible is trying to kill them. Space radiation is not like the radiation on Earth. Beyond our planet's protective magnetic field, astronauts are bombarded by galactic cosmic rays, high-energy particles flung across the universe by dying stars and distant supernovae. NASA's own radiation assessment detector, carried aboard the Mars Science Laboratory in 2011 and 2012, measured the round-trip radiation dose at 0.66 sieverts. NASA's career radiation limit for astronauts is 1 sievert, and that number accounts for a lifetime of exposure, not a single mission. A full round trip to Mars, including time on the surface, pushes right against or beyond that ceiling. NASA's Human Research Program estimates that radiation-induced mortality and health risks could exceed 5% to 10%, with upper confidence intervals approaching 20%. That means before you factor in any accident, mechanical failure, or medical emergency, just breathing the air inside the spacecraft carries a 1 in 10 chance of eventually killing you. But here's where it gets worse. Even if an astronaut survives the radiation of the journey, their body is quietly dismantling itself in other ways. Muscle tissue begins disappearing within days of leaving Earth's gravity. Research published in peer-reviewed journals shows that up to 20% of skeletal muscle mass can be lost in a single month of microgravity, with muscle strength dropping by as much as 30% in the same period. Astronauts aboard the International Space Station exercise for 2 full hours every single day just to slow this process. They don't stop it, they slow it. And here's the brutal detail no one talks about. Mars's gravity is only 38% of Earth's, well below the 0.67 g threshold that new ISS research published in early 2026 identifies as the minimum needed to prevent muscle deterioration. So even after landing, the atrophy doesn't stop. It just changes pace. Every day spent on Mars is a day the human body continues drifting further from the physical baseline it needs to survive on Earth. Bones tell an equally grim story. Studies modeling bone mineral density loss across a Mars mission predict that 100% of astronauts on a longer conjunction class trajectory, lasting 1,000 to 1,200 days, will develop osteopenia. 1/3 are predicted to reach full osteoporosis. These are not speculative risks. They are mathematical projections built from real data collected on ISS crews. The body that boards the return spacecraft after a year or more on Mars is not the same body that left Earth. It is lighter in all the wrong ways. Frailer, more brittle. And the return journey, another 7 to 9 months of radiation and microgravity, would stack damage on top of damage. Now consider the return window itself. This is where the trap fully closes. You cannot simply decide to come home from Mars. The orbital mechanics of the solar system do not care about your plans. After arriving on Mars, astronauts would need to wait on the surface for roughly 18 months before Earth and Mars realign enough to make the return trip feasible. The alternative is a short, opposition-class mission of around 400 to 600 days, but the fuel cost is enormous and the radiation exposure during those longer arcs through deep space spikes dramatically. Either way, the traveler is locked in. There is no emergency exit. There is no rescue mission standing by. If something goes wrong, a medical emergency, an equipment failure, a mental health crisis, Earth is between 3 and 22 minutes away by radio signal alone. By the time Houston receives your distress call and responds, nearly an hour may have passed. The landing on Mars of NASA's Perseverance rover in 2021 illustrated this perfectly. The entire landing sequence had to execute autonomously because the 11-minute communication delay made real-time human control physically impossible. Now imagine that delay during a surgical emergency on a human crew. And then there's the mind. NASA's 𝐃𝐨𝐽 simulation, a year-long Mars analog mission that began at Johnson Space Center in October 2025, placed 4 crew members in an isolated, confined habitat to study exactly what happens to human psychology under these conditions. What researchers found confirmed what decades of isolation studies had already suggested. Prolonged confinement in a small space, cut off from Earth's natural rhythms and social connections, produces measurable cognitive decline, interpersonal friction, and psychological deterioration. The farther from Earth, the worse this becomes. Astronauts on the ISS can video call their families with a slight delay. Mars crews would have conversations that take 20 to 44 minutes just to complete a single exchange. Imagine calling home and waiting half an hour for a reply. That is not a conversation. That is sending messages into a void and hoping something returns. And the environment waiting for them on the surface offers no comfort. Mars is not a dormant, quiet world. In September 2017, NASA recorded radiation levels on the Martian surface temporarily doubling due to a massive solar storm, with auroras 25 times brighter than anything previously observed. The thin atmosphere, roughly 1% the density of Earth's, provides almost no protection from solar energetic particles. In 2026, NASA's ESCAPADE spacecraft are en route specifically to study how Martian space weather behaves, because we still don't fully understand what a future human crew would face during a major solar event on the surface. The answer, based on everything gathered so far, is a great deal of danger. So now add it all together. 7 to 9 months of radiation exposure just to arrive. 18 months waiting on a surface where your bones soften, your muscles waste, and a single solar storm can spike your radiation dose to dangerous levels. Another 7 to 9 months of the same punishment for the return. A total mission length of somewhere between 2 and 3 years. And a human body that, by the end, may simply be unable to readapt to Earth's full gravity. The cardiovascular system, long relieved of the burden of pumping blood against a full 1G, may no longer manage it properly. The skeletal structure, hollowed by months of reduced gravity and radiation, may fracture under what was once routine movement. The vision, frequently impaired by fluid shifts in microgravity, a condition NASA calls spaceflight-associated neuroocular syndrome, may be permanently altered. This is why serious scientists, not science fiction writers, speak openly about Mars as a one-way proposition. Not because the technology to return doesn't theoretically exist, but because the human body may not survive the round trip in any meaningful sense. You might physically make it back, but the person who returns, the cardiovascular system, the skeletal structure, the cognitive function, may be so fundamentally changed that coming back becomes a philosophical question as much as a physical one. That isn't the end of the conversation. It's the beginning of a harder one. NASA is developing nuclear thermal propulsion, a technology that could cut transit time to roughly 4 months, dramatically reducing radiation exposure during the journey. Research into pharmaceutical countermeasures for bone and muscle loss is advancing. 𝐃𝐨𝐽 and its successor studies are mapping the psychological terrain of long isolation. Every piece of this puzzle is being worked on simultaneously because the alternative, abandoning the ambition entirely, is not in the human vocabulary. But the honest truth in 2026 is this: we do not yet have the tools to send a human to Mars and bring them back whole. The planet is not waiting for us with open arms. It is waiting with radiation, emptiness, silence, and physics. The first people who go will likely know, going in, that the mission is more permanent than any mission in history. They will go anyway, because that, too, is in the human vocabulary. The question is not whether someone will eventually stand on the Martian surface. They will. The question is whether we have the wisdom to solve the biology before we solve the engineering, because right now, the rocket is closer to ready than the body is. And somewhere in that gap, between the ambition and the biology, lies one of the most fascinating and terrifying frontiers the human species has ever faced.